Welcome to Saucy Math. This is a video about radical expressions and combining and simplifying expressions that involve radicals. So the first one we're going to look at here is the square root of 10 times the square root of 32. All right, so one of the properties of radicals is that you can multiply them together as long as they're the same root, like a square root times a square root. You can just take those numbers inside and multiply those together inside one big square root. Right, what you can't do is if you have like a fifth root times a third root, those you can't just multiply together. But as long as the roots you're taking are the same, you can just do this. The square root of 10 times the square root of 32 is the square root of 10 times 32, which is the square root of 320. All right, so we combine those two radicals into a single radical with a bigger number inside, 320, and now what we need to do is try to simplify the square root of 320. All right, so now we get into simplifying this root. Now, to do that, you might want to have what I have over here on the right, a list of the perfect squares, so like 1 squared equals 1, 2 squared equals 4, and so on. I went down to 10 squared equals 100. Generally, that's about as big as you'll need, unless your teacher is like a real jerk and wants to give you like huge numbers that you have to work with, in which case you may need to extend this list a little further down to find the numbers that you want to work with. Right? But what we want to do here is look for a perfect square that's going to divide evenly into 320. Right, and there are actually a couple here that are going to do that, and we want to find the biggest one possible. Right, so 1 obviously is going to divide into everything, so that's not really going to help us though. 4 will divide evenly into 320, but let's see if there's a bigger one we can use. 9 is not going to work, but 16 will. Right, but actually, if we go way down here to 8 squared equals 64, that's going to be the biggest of the perfect squares that divides evenly into 320. All right, so what we're going to do is rewrite the square root of 320 as the square root of 64 times 5. All right, because 64 times 5 equals 320. All right, and now we can separate this kind of like what we did in that first step, just going backwards. That's the square root of 64 times the square root of 5. And the square root of 64 we know is 8. So we get 8 times the square root of 5. Right, and the square root of 5 we cannot simplify anymore because we don't have any of these perfect squares here other than 1 that's going to divide into that 5 evenly, so we can't simplify that root anymore. All right, so we get the square root of 10 times the square root of 32 equals 8 times the square root of 5. All right, so that's how you approach these types of problems. When you have to simplify a large number inside the root, you look for one of these perfect squares that divides evenly into that, and then it's almost like you can pull out that perfect square. All right, the next one we have, the next example, we have the square root of 54 divided by the square root of 6. All right, similar like the rule from example A for multiplication, the same thing applies to division. So the square root of 54 divided by the square root of 6 is the square root of 54 divided by 6. Right, since they're both square roots, they're the same root that we're taking, we can just combine them together into one single root and do the division inside the square root. And 54 divided by 6 is 9. Right, so we end up with the square root of 9, and then the square root of 9 just equals 3, right? Because 3 times 3 equals 9. Right, so that one wasn't as difficult to simplify as this one was, where we had the square root of 320. This one was just pretty direct, the square root of 9 equals 3, and we were done with it. So that's always nice when it works out that way. All right, the next example we have is the addition of two radicals. Right, we have the square root of 125 plus the square root of 45. So we cannot add radicals together unless they have the same number under the radical. All right, so we can't just add together the square root of 125 and the square root of 45 and that may make that the square root of 170. It just doesn't work that way. But we might be able to add these together if we can simplify them, kind of like what we did up here with the square root of 320. If we can simplify them somehow and we end up that they end up with the same number inside the root, then we would be able to add those together. So the square root of 125, we're going to look at our list of perfect squares, and it looks like 25 is the perfect square that we can divide evenly into 125. All right, so I'm going to write the square root of 125 as the square root of 25 times the square root of 5, right? Because 25 times 5 equals 125. Plus, and now I have to try to do the same thing with the square root of 45. So now we look at our list over here of the perfect squares, and do any of these divide evenly into 45? And 9 does. Right, so I can rewrite the square root of 45 as the square root of 9 times the square root of 5, because 9 times 5 gives me 45. Right, and you might already see what's going to happen here. Right, the square root of 25, that equals 5. All right, so we have 5 times the square root of 5 plus, and then the square root of 9 is 3, so we get 3 times the square root of 5. And now we can add these together because the numbers inside the radicals match up. Right? I can add 5 square root of 5 plus 3 square root of 5 because they both involve the square root of 5. Those are like terms now. Right? The square root of 125 and the square root of 45, those were not like terms, so I couldn't add those together back then. All right, and to add the radicals together, basically I take the numbers outside, kind of like adding 5x plus 3x. You just add the numbers and you make it 8x. Same deal here. 5 radical 5 plus 3 radical 5 equals 8 radical 5. Right? You add the numbers outside the square root. The number inside the square root doesn't change. Just like when you add 5x plus 3x, you don't change the x, you just make it 8x. Right? So it's the same idea there. All right, the last example we're going to look at here is subtracting 2 cube roots. Right? So we have the cube root of 54 minus the cube root of 16. Right, so this one's similar to the last one we did. We cannot just subtract these because the numbers inside the radicals don't match up. So now, since we have cube roots, we want to look at the list of perfect cubes that I wrote over on the right here and see if any of these perfect cubes will divide evenly into the numbers we have underneath our cube roots. Right, so here I went from 1 to the 3rd power down to 6 to the 3rd power. Again, generally that's about as big as the numbers you're going to need unless your teacher wants to give you a really big number and make your work a little harder, in which case you can just keep extending this list, as far as you need to go. All right, so our first cube root we have is 54, so do any of these numbers, again, other than 1, do any of those numbers divide evenly into 54? See, 8 won't, but 27 will, right? Because 27 times 2 gives us 54. So I can rewrite the cube root of 54 as the cube root of 27 times the cube root of 2, right? Again, because 27 times 2 gives us 54. And then I'll try to do the same thing with the 16, right? Do any of these numbers divide evenly into 16? And 8 obviously does, right? 8 times 2 equals 16. So then we have the minus, and then the cube root of 8 times the cube root of 2, right? Because again, 8 times 2 gives us that 16 that we had up there. And now I can take the cube root of 27, since that was on my list of perfect cubes over here, right? 27 is 3 to the 3rd power. So the cube root of 27 is 3, and then times the 3rd root of 2, minus, and then the cube root of 8 is 2, right? Because 2 to the 3rd power equals 8. So it's 2 times the 3rd root of 2. And now, just like in that last example we did, the numbers inside our radicals match. We have the 3rd root of 2 and the 3rd root of 2. Now we can combine these terms together because now they're like terms. And just like with the last one, we just do whatever the operations say with the numbers outside the radicals. So we have a 3 out here, minus a 2 here. 3 minus 2 equals 1. So it's 1 times the 3rd root of 2. And just like when you have like a 1x, you don't write 1x, you just write x. I'm just going to write that as the 3rd root of 2. All right, so that's a few examples of doing some operations with radicals and simplifying radical expressions. That's it.